All right, so this is another requested video. Again, it is in Danish, but I'll tell you what's going on. So in this problem, what we're asked to do is sort of take this NMR spectrum, and I believe what we're supposed to do is assign the given spectrum. So we've got the proton NMR spectra here, and then we've got a zoom in of the aromatic region, so we'll talk more about that in a second. And then I've just recreated the molecule here. So given this molecule, can I assign this NMR spectrum? And that's what we're going to do. So for this, again, the first thing that you're always going to want to do is to figure out, the different chemical environments, the different protons that you have, and how many you have, and sort of give them a label. So I would start out here with these methyl groups. So I'm going to put, my 3 little hydrogens out here. So off of this CH3, we'll call these A. Over here, we're going to have, again, 3 protons. We'll call those B. I've got a single proton here. We'll call that C. I'm going to label these 2 protons off of my aromatic ring as D and E. And then my NH2, we'll call those F. So that's the first step, just sort of identify the different, protons that you're going to have. Right away, we could think about the integrations, right? This should be 3 high, 3 high, 1 high, 1 high, 1 high, and 2 high. So that will help us get going, right? Right away, we can look at this NMR spectrum. We can say, oh, looks like we've got 2 big peaks here. They're roughly the same height. So these are probably both of our A and B. We can see that right away. Now, in terms of deciding which one of these is A and B and getting going with the actual assigning, I'm going to look what the chemical environment is, right? This B is bonded to an oxygen. That oxygen is going to shift this peak downfield. So I'm going to label this one as B and this one as A. And I think those are a good starting point, sort of an easy way to get going. Now I'm going to look at these remaining 4 peaks. And really, these sort of look all, they look all about the same height, right? They're pretty similar. I clearly have a doublet of some sort here, a doublet of some sort here. This looks like a singlet. We do have a zoom in, right? So we can zoom in on this region here. So we'll look at that in a little bit more detail in just a second. But I want to talk about this peak here. So I know that this is going to be the peak for F. And I've got a variety of reasons for saying that. I think probably the best reason is that it's a little bit broad. So to me, because it's broadened, that suggests that this would be an integration of 2 high, which is a little bit crazy, right? This is just so much taller, but because this is broadened a little bit, the integration is the whole area. So this, I think, is pretty clearly going to be my NH2 peak. It's also sort of in the middle here. It's not really in the aromatic region. I figured this would be more aromatic region. This is somewhere in between, from where we see our, CH3 groups here. So I think that's pretty clearly F. Now for our zoom in region here, I'm going to put it like this. I've got C, E, and D. Now, C is going to be close to a singlet, right? It's going to be the thing that most resembles a singlet. And I say most resembles because this is our peak for C, and there is a little bit of splitting here, right? There's a very fine coupling there, but it does look, versus these other 2 peaks, this is clearly C, right? And I would expect C to be a singlet because on the adjacent carbons, there's no other hydrogens, right? And we'll talk about this fine coupling in just another minute. Now E and D, they're going to split one another, right? So E and D, we're going to get some splitting between them because this proton D is going to be split by E, E is going to be split by D. So these should look as doublets, right? And then in fact they do. We do see 2 doublets here. Now deciding which one is which, right? Which one is E, which one is D, that's going to be a little bit more complicated. And the way that we're going to solve that is actually going back to this fine coupling on C. So C can actually couple with E. It's called a meta splitting, right? We're through this ring. So E can also couple with C. So if I look at these 2 peaks, this one, I also see that fine coupling, right? That really small, probably about 2 Hertz coupling, very, very small coupling. So to me, these 2 must be linked, right? These 2 are interacting with one another, they're splitting one another, and this one is not. And so if I look here, well, I know that this one is C. So then, which one is C most likely to interact with? Well, C is most likely to interact with E because it's the closest, and that would be the meta splitting. So I'm going to say that this one is E, and this one then would be D. So putting it all together on this picture, this one is C, this one is E, and this one is D, and that should be it. All right, if you have any questions, definitely let me know in the comments below. Thanks very much.